Now we want to explore mean and median a little bit more. Suppose we have one new class member. They showed up late for class. We have to add them into our data set. And they have 127 pets. And this actually happened. This class actually had a student in the class that had 127 pets. It was 3 cats, and the remaining ones were tarantulas because they were involved in a science experiment. So they had a bunch of pet tarantulas. It was huge. All right. So what does this person do to our graph? So here's the graph. I kind of crammed it in over here. It's not great still. There's the mode, right, because it's still the tallest bar, which is 0. There's the outlier at 127. So we have our 6 dots at 0, 1 at 5, or excuse me, 5 at 1, 5 at 2, 5 at 3. There's the 4, the 5, the 6, the 7, and the 14, right, or the 8 and the 14, right? So it's not to scale, but, or the, excuse me, the 8 and the 18. Oops, except there was no 18. Sorry. It was even smaller a graph than that. It was very small. Okay, so it's all crammed in over here. So what happens when this person gets added to our group? What will happen now to our mean, our median, and our mode? Okay, well, let's look at it. So the median used to be an empty space in between 2's, right? It used to be here. That used to be the median. But let's look at what happens now. With the mode, it'll still be, actually, before I even go any further, I can actually tell you the mean we need to look at. The median is easy to figure out, and the mode is easy to figure out. The mode is still 0, right? Because the height of the bar hasn't changed. This one outlier does not affect it at all. The median, it's a little easier to see if I go back to the list so you can kind of see it. So the median was here. It was this empty space between these two. If I add in 127 over here at the edge, what that does is it nudges the median over from here to over here. And this value now becomes the median. So the median, for example, 1 was the green one. So the median for example 2, when I have the 127 in there, is now the red one. But as you can see, it's still the same number. Right? It doesn't really affect it much. Now it could nudge it a little bit. I mean, sometimes you could get nudged from a 2 to a 2.5, or from a 2.5 to a 3, something like that. But this one just nudged it from a space, which was 2, to this spot, which is 2. So if you look at it on the dot plot, it's going from this line to this. That is now the median. Well, it's still 2, right? So 2 pets still. But the mean is not going to be the same. So let's go to StatCrunch for a second. I'm going to add in, I'm going to scroll down here and add in a 127 here at the bottom. And I'm going to rerun this data set. And the way you can do that, if you already have it run, is to click Options and then Refresh. And it'll run it again, but with the new number in. And you can see the mean jumped. The median stayed at 2, the mode stayed at 0, but that mean jumped to 6.89. Which, if you think about it, is not a fair representation at all of our data set. Okay, what's happening? Well, because the lever has to extend all the way out here to accommodate this outlier, where we would put the fulcrum now went from where it was, which was 2 point something, to this new value, which is 6.89. So it's in here. This now becomes the mean. It's the balance point. And because we had to go far out to balance that outlier, that one that lies far out from the rest of the group, it caused our mean to get pulled right. So this has moved significantly higher than it was. The other two stayed the same. I mean, technically the median nudged a little bit, but it didn't matter because it was the same value. So what do we notice? Well, we notice that the mode and the median are not affected at all or affected very little. Um, I'll just say not affected. Well, the median does get nudged a tiny bit, so affected just a little bit, right, by the outlier. But the mode, or excuse me, but the mean was affected drastically, was pulled from 2.89 pets to 2.27, even worse, 2.27 pets to 6.89 pets. Okay, this leads us to our first big concept about mean and median and mode, which is that the mean is sensitive to outliers, right? Outliers affect the mean greatly, but they don't affect the median and the mode. So the median and the mode are said to be resistant. Oh, if I could spell the word correctly, resistant to those outliers, right? Because they were only affected a little bit or maybe not at all, they are resistant to the pull of an outlier, whereas the mean is not resistant. An outlier can have a great impact on the mean. So if that's the case, and a mean can get greatly pulled by an outlier, that affects what measure of center is a better representation for our class's pet ownership. So if the data are skewed, right, if the outlier is included, so if there's no outlier and the data are pretty symmetric, I'll just write that data symmetric, question mark, then the mean is probably best because it includes all of the data sets, right, all numbers included. And it's what people think of when they think of average, right? But if there is an outlier or the data are skewed, and it's possible for data to be skewed but not have outliers. But if either one of those things is happening, then the median is best because it's resistant. It's resistant to outliers. It's resistant to the pull of a skewing. Measures of center, by the way, is just another fancy word for average, right? So what's the center of our data set? What's the average for our data set? So that's important point number 2. When the data are skewed left or skewed right, the median is the better measure of center. We'll learn more about that in another section. Actually, it says section 3.4, but I think it actually means section 3.5. All right, and we'll add to this table in section 3.5. Sorry, that's a typo there. I'll fix that typo for later. All right, so let's look at the table here. So if it's skewed left, the mean is less than the median. It's got the pointy end. So the mean is this one over here. That's the mean. And the median is this one. So that's what that symbol means. It means the median is less than, the mean is less than the median. So the mean is less than, which is this symbol, right, the median. All right, if that's the case, we call that skewed left. When your mean is significantly less than your median, that's skewed left, and your better measure of center is the median, because the median resists the skew. Oops, again, if I could spell resists correctly. Resists skewing. Right? Okay, let's jump to the bottom actually. What if it's skewed right? Well, if it's skewed right, the mean will be pulled over here. This is the mean. The median will be right here, right? The mean gets pulled towards the tail. So this is skewed right. The tail is what makes it skewed. So the mean is greater than the median. Greater than is this symbol, right? I just realized I thought I cleaned that up. Less is this symbol, greater is this symbol, right? So mean is greater than the median, right? So if the mouthy end is eating the mean, then it's bigger. And then again, the median would be the better measure of center because it resists skewing. Okay, but what if they're the same? What if your mean and your median are right next to each other? Really, really close. Might not be perfectly close, but pretty close. Okay, well then what? Well then that's symmetric. It might be bell-shaped like this one. It might not be, right? Remember, you can be symmetric in a lot of different ways, but it'll have that kind of shape. And that means that the mean is approximately equal to the median. This squiggly equals means approximately the same, or approximately equal. Now, how close is close enough? That's a judgment call you have to make when you look at the data set and try to figure out if the numbers are close enough, right? So what counts as approximate, what counts as greater than, is a judgment call. So I'll make a little note of that down here. So approximate versus greater than versus less than is a judgment call based on the size of the numbers in your data set and the real life values of what's going on. So there's no hard and fast rule for how big is big enough to be skewed right or skewed left. Right? You just kind of have to look at them and look at the data set and say, oh, I think it's big enough. That's also where graphs can come in handy, because if you can graph it, you can also kind of see, oh, okay, I think it was skewed, and it is. Okay, so if they are approximately equal, then it's a symmetric graph, in which case the mean is the preferred one. That's because when it's symmetric, we can do a lot more with the mean. There's a lot more formulas based on the mean and various other things. So we would rather work with the mean if we can. And we often do work with the mean. And we can get away with that when the data set is symmetric. There's a lot of this course that's built on the mean. So if we can use it, we want to, right? We don't have as much, mathematically speaking, for the median. But the median's better than nothing if your data set is skewed. Then you have to use it.